Alright, in this video, we're going to talk about using some of the results that we have, especially the prime factorization theorem, the fundamental theorem of arithmetic, to come up with a method of determining if a number is prime. So let's call this, I guess, theorem, I believe it's section 40.1, and it says the following. If n is composite, remember composite means that it's not prime or 1. That's made up of 2 or more prime factors multiplied together. So if n is a composite number, then n has a prime factor, p that's less than or equal to the square root of that number. And that's a really useful fact. If you think about it, square roots are quite a bit smaller than numbers themselves. So to determine if a number is prime, all we'll have to do is we'll have to check all primes below or equal to the square root of that number. So let's go ahead and prove this. So again, this is going to be by contradiction. We're going to pretend like there's a counterexample, and we're going to show that something blows up. So we're going to assume there is a counterexample. So assume that n is a composite number. So it is made up of 2 or more prime factors, and that's going to be key for us, and the negation of the then part. So n does not have a prime factor that's less than or equal to the square root of n. So and all prime factors are greater than the square root of n. Okay, so that's what a counterexample would look like. Now, what does that mean? So since n is composite, well, what does that mean? It has at least 2 prime factors. They could be the same, but we'll call them P and Q, and they're both, let me put a comma instead of a dot there, sorry. P and Q, which are greater than the square root of n. And you can kind of see what's happening here. So we know that n equals P times Q times some other stuff, C for some C in the natural numbers. And just to be clear, so as a quick example, I'll erase it in a second, but if n was 24, no, let's not do 24, let's do 60. If n was 60, well, 60 is 2 times 30, or 6 times 10, so that's 2 squared times 3 times 5. And the square root of 60 is 7 and a bit, we'll say. But I'm going to pick 2 prime factors. But you can see none of these are greater than the square root of n, but the idea is I'm going to pick 2 of them, and then whatever's left over, this is going to be your C. So that's all I'm saying there. So whatever 2 prime factors, it could be the same. In fact, I could have picked 2 twice in the previous example, and that would have been fine. All right. So n is our 2 primes, because we know 2 of them exist because the number is composite, times everything else. But, oh, that's not the color I want. Here we are. So n, which is p times q times c. Well, if I replace p with square root n, well, I know p is greater than square root n, so if I replace p with square root n, I get something smaller. And same with q. Q is also greater than square root n, so if I replace q with square root n, I get something smaller again. So let's do that. I get something strictly smaller. I get square root n times square root n times c. And we can simplify that. Square root n times square root n is square root n squared, which is n times c. And we know c is a natural number, so if I don't multiply by c, well, I get something at least as small as n. Okay. So, putting this together, what did we show? Look at this. This is wild. We started with n, and we got that it was greater than, and we ended with n. You can see all these inequalities are all greater than inequalities. So we're not switching inequalities anymore to the same direction. So this n is greater than that n. So we get that n is greater than n. But n is never greater than itself. There's our contradiction. So since n equals n, of course, n greater than n is a contradiction. It's something that's always false. So if we have that, we can say thus, there are no counterexamples. And the theorem must be true. So we've shown it. If it has no prime factors less than or equal to the square root of the number, then the world blows up. We get that n is greater than itself, which makes absolutely no sense. So, let's move on. Let's use this now. It's most useful in the following form, in its contrapositive form. So the contrapositive of theorem 40.1, we don't have to reprove it. Contrapositives are logically equivalent. But let me just write it. So it says, if n has no prime factors, that are less than or equal to the square root of n, then n is, I'll write it like this first, but then I'll erase it, not composite. But if n doesn't equal 1, really, we could say, and thus n is prime if n isn't 1, which nobody would ask you, is 1 a prime number? Remember, 1 is neither prime nor composite. So we can even just think of this as saying n is prime. So that's a good way of thinking about it. So that's kind of the most useful form of that theorem. So let's go ahead and do an example with it. So let's check, is the number 641 prime? And in general, deciding if a number has factors and what these factors are is a hard problem. Multiplying two factors together to get a number is easy, but figuring out what factors you multiply to get a number is much, much harder. And in fact, I don't want to go into this in too much detail, but most of our encryption is basically based on that. That multiplying numbers together is easy, and figuring out what two numbers give you the certain number when multiplied is very hard. So this, in some sense, is a hard problem. Well, let's use our theorem here. We need to figure out what the square root of 641 is. Well, if we have a calculator, we can do that. But if not, we can just estimate, figure out what it's between. I know 25 squared, you can check with the calculator, is 625. Or you could just do it on paper. And 26 squared is 686. Okay, so 641, the square root of it must lie in between 26 and 25. So, what prime numbers do we need to check? We need to check primes. Well, 2, 3, 5, 7, 11, 13, 17, 19, and 23. So that is 1, 2, 3, 4, 5, 6, 7, 8, 9 different primes we have to check if they're a factor. Okay, so is 2 a factor of 641? No, that's pretty obvious. You can always check these by long division. There are some rules some divisibility rules that'll help you out as well, if you know those. So is 3 a factor? Let me use this, give myself a little more room, and use this question mark notation. Okay. Is 3 a factor of 641? You can check by long division, or if you add up the digits, if the sum of the digits is divisible by 3, then the number is divisible by 3. But 6 plus 4 plus 1 is 11, so that's no good. Is 5 a factor of 641? It is not. Doesn't end in a 5 or 0. What about, I'm going to skip 7. Let's do 11. Is 11 a factor of 641? Well, you can check via long division, or if you know that if you take the alternating sum of the digits, then, and that sum is divisible by 11, then the number is divisible by 11. So 6 minus 4 is 2, plus 1 is 3. 3 is not divisible by 11, so fortunately not. And they're kind of the only easy divisibility rules. 7 has a divisibility rule. Let's check that. 641's a little bit harder. But if you take the last digit here, multiply it by 2, and subtract it from everything beforehand, then that's what you can check. So we have 1. So 1 times 2 is 2, so 64 minus 2 is 62. Is 7 a factor of 62? Of course, it is not. So 2, 3, 5, 7, 11 are not factors. We need to check the other ones. No nice divisibility rules for the others, so we just do long division. So 13 into 641. 13 goes into 64. Let's try 4 times. And we get 52. Subtract, we get 12. 13 goes into 121. Let's try 9 times. So that is 7, carrier 2, 117. Remainder 4. So 13 is not a factor of 641. And we can keep going with the others. Let me just scroll up here. Oh, that's not scrolling. There we go. So let's check 17 into 641. 17 goes into 64, let's say 3 times. 3 times 7 is 21, carry your 2. 51, subtract, we get 13. 17 goes into 131. I don't know what to try. Let's try 8 times. 7 times 8 is 56. Carry your 5. That's 13. That's too big. It's going to be one less than that. But you can already see we get a remainder of minus 5. So the remainder, when we divide 131 by 7, is not going to be 0. So it's 49. So 4 here instead. 11, subtract, we get 12. So 17 isn't a factor of 641. We have 19 and 23 left to check. So we'll just do 19 over here. Well, 20 goes into 64 3 times, so 19 probably goes 3 times as well. That is 57. Subtract, we get 7. 71. Let's try 3 times again. Subtract 57, we get 14. So 19 isn't a factor of 641. And finally, we have 23. I'll just check that. So is 23 a factor of 641? I don't know. 23 goes into 64, let's say twice, minus 46, that's 18. And it goes into 181, let's say 7 times, 8 times, let's try 7. 7 threes are 21, carry your 2, 161, with remainder 20. So it looks like 23 also isn't a factor of 641. So, after all that work, that's just scratch work. I can erase that now since this is a video, but I was just checking if 13, 17, 19, and 23 were factors of 641. And if you didn't know the divisibility rules, you could do long division for these guys as well. But for our purposes, let's just erase this. And we can say, well, we've checked all possible primes that are less than or equal to the square root of that number. Thus, 641 must be prime. So you can see kind of the power of this. Otherwise, you'd be wondering, just checking random factors, random numbers. But if you know this result, then you know exactly what 9 numbers you would need to check if they're divisible. So that is great. It's a good time saver. And hopefully it helps you guys kind of understand the idea of the fundamental theorem of arithmetic a little better as well.